Hey guys, today I'd like to show you how to do a first and second order analysis of a simple fixed beam on Autodesk Robot Structural Analysis 2015. This will be done in US customary units, unfortunately, for you that are those of you who aren't in the US. Um, this is being done so that you can extend it for larger structures and you'll be able to understand how the analyses are done. So first of all, we're given our area of 1,000 inches squared, or modulus of elasticity, Young's modulus of 30,000 KSI, and our moment of inertia about the x-axis as 200 inches to the fourth. There is a load of 200 kips at midspan. Total length of the beam is 200 inches, and there is also a axial load of 2,500 kips. Okay, so let's go ahead and fire up robot. To show you here, I did the exact analysis of the beam with the same numbers that I showed you on the AutoCAD file just now. So we'll be able to compare it to what the exact values are, and that is why I chose such a simple problem. So we're going to go ahead and choose new project. I'm not sure what you have down here, but we're going to end up doing a frame 2D design. You can go to File, New, and here you have your other options. So we're going to click on Frame 2D Design. Once we're in that, when you start up robot for the first time, you're probably going to be in metric units. So we're going to have to go in and go to Preferences. And in here, Regional Settings, it'll be set at Eurocode as the default. Eurocode, it'll give you British English, and everything will be in British English. And this is the code that's common in Europe. But since we're here in the United States, we're going to stick with that. Go to Accept. So here you can see that my default units are in kip feet. And since our problem statement is in kips and inches, I am going to change that. So double click. And here it comes up. Change this to inches. Also in my forces, I'm going to change this to inches, and then I have no particular reason just for changing it to kip inches. That's only because my exact results are in kip inches. I haven't changed it. As you could see, my units changed. It went from feet to inches. So this was -20, it went to -200 inches. So now we're going to have to define a grid. So let me start with the Z. We only need one since it's only a beam, one single beam. We're gonna just press add. And then for X, we need the number of repetitions to 1 and the distance is 200 inches. If I had changed this down here, then this distance would be in feet, and you can double click in robot in the text box right there, and you can actually say, for example, you can put in an equation. 200 divided by 12 equals 16.6667 feet. So that's if I was going to put it in feet, and you click OK and it's in there. But since I'm going to be doing inches, I can just do that. So click add. It's good practice to label your axis differently. So I'm going to change that to an ABC. Click apply. And as you can see, my axes are now here. So the next thing we're going to do, we're going to define our material. So go to Tools, Job Preferences, Materials, Modification, go to Other. Sorry, I already have this one put in from a previous time. But you can type in the name you want here, change this to 30,000, which it was already from my previous work, and make the force density 0. So I'm going to click OK. If you were making this for the first time, you'd click add, and then click OK. So OK. So next we're going to create a bar section. Just a note, you could click materials from, You can change the materials from in here. Maybe not. Okay, bar sections. We're going to create a new bar section, and they see they have all the regular stuff like an I-beam, channel, angle, um, and they have it for so many options for concrete or steel or whatever is it you want to do. So I'm going to label this tutorial 1. Tutorial 1. And our area from the problem statement was 1000 inches squared. 1000, or IY is 200. As you can see, Y goes into the paper. So that's going to be our axis of bending. So that's equivalent to our IXX. So we're going to go ahead and I'm going to change these to 1 just so that robot doesn't give me an error message once we do the calculations. It would be best to leave these as 0 because that would remove any shear deformation from the calculations. So I'm going to go ahead and click add. You can't change the section type. It has to stay as one of these. There's no other. So add, close. Okay, so now we're ready to draw our bar. So geometry, beams, steel beam tutorial 1. Click on this node and click on this node. And our beam is drawn. So one thing I want to point out, if I click to the left of the midpoint, then the arrows point to the right. If I hover over the bar that's to the right of the midpoint, then the arrows point to the left. This is actually, I've only seen this in robot, but that allows you to the initial node and the final node change depending on what part of the member you click. So that's very helpful in terms of defining loads and that stuff. So we're going to go ahead, click the member, and go into the properties right here. See our material is steel. Let's change that to tutorial 1. So right now, the next thing we have to do is define our supports. So it's on fixed right now, so we can just click the point. Let me make a note to you guys. So this is modeled as fixed, but in order for this axial load to be transferred into the beam, we can't model this side as fixed. So I'm going to make this some other support. I don't really have a name for it. It's like a sideways roller or something. So we're going to change this into another support and keep this as fixed. And that will allow the axial force to go into the member and create the second order forces. So to create a new support, you click here, new support definition. And we're going to unlock UX, that's translation in the X direction. See, X is this way. And click add. Let's change this to tutorial 1. Tutorial 1. Add, close. And where tutorial 1 is selected, click. Alright, it's all there. So now you can see my supports, they disappeared. So down here you can just click support symbol. Here has all the other things that you can toggle as it pertains to views. You can toggle the load symbols, the section shapes, support symbols. So I'm gonna turn them on because I like to see what I'm doing. So we're gonna define some loads now. Load types. So I'm just gonna add an arbitrary load, click add. So when you do this, a robot structural analysis, it takes into consideration the self-weight of the beam, or whatever is in the self-weight of the entire structure, to be exact. So what I'm going to do, since I want to neglect the self-weight, I'm going to delete this. And I'm going to create a new one, which is called vertical. Add. See, now negative PZ is gone, so the self-weight is no longer taken into consideration. Just a note, I could have done the vertical and the lateral in the same case, because I'm not going to use any load factors for this, no safety factors. So it's going to be equal to the same thing, but when I do them separately, it makes it easier so you can view what load is caused by each load case, or what forces are caused by each load case. My bad. So here we have vertical, then I'm going to do 2 lateral, and then add, then close, and let me do manual combinations. You could do automatic combinations, and it has LRFD, ASD, all that good stuff, but we're not going to do that for this problem. We're going to do manual combinations. This will be combination number 3. Let's call this linear. This is for the first order analysis. ULS, SLS, ACC, this isn't gonna matter because I'm using a load factor of 1, so it doesn't really matter. So we can go, okay, parameters, you can leave those as is. Okay. So to define the linear load case, we're going to make those both 1. Now I could click this and it would send them over with the load factor individually, or I could click this and it'll send over all the load cases with that load factor. So click that, apply. So I'm going to click new load case. 4 is going to be nonlinear, which is second order, and ULS, okay. And I could choose both vertical and lateral and send them over with a load factor of 1, or I'll just choose linear. Sorry, linear and send it over with 1, and bam, apply, close. So now you can see all my load factors are in here. I'm going to go to analysis types right here. I'm going to double click. So this is where you have to be careful. Auxiliary case, that means it doesn't run pretty much. Robot just doesn't take the case into consideration. It's just there for being there. Nonlinear analysis is what we're accustomed to, or most engineers are accustomed to. That's what's required by AISC, second order analysis, and this would include P little delta and P large delta. P delta analysis refers to third order analyses, which isn't used much by engineers. It's important, but it isn't used as frequently as second order analysis, which is what nonlinear analysis is. So we're going to go ahead and check that. Parameters can stay as they are, and click OK. So close, static, linear, nonlinear, close. So I think it's time to do the load definitions. So load definitions, you could come here, you could come up here, doesn't matter. So we're going to go on the bar, click concentrated load. So we're going to have a force of negative 200 kips, see the values in kips. And I'm going to do this with respect to the global axis. X equals 0.5 relative, which means just 0.5 of the 200 inches. Let me just show you what I was talking about earlier with the position being changed relative to where you click on the bar. So click add. If I click it from this side, then it's going to be right here. And if I do it from this side, it'll be right here. So it changes depending on where I click on the bar. So let's change this back to 0.5 and relative, add. Okay. And, ooh, sorry, my bad. We're going to have to delete all those. It's not showing up the load, so I just click that little button down there, right click, delete for objects from this load list. Okay, what? And then delete. So I am deleting those because I put them on as lateral load, which I never wanted to do. I wanted them to be vertical. So negative 200, add, bam. Okay, next we'll go to node, come here, negative 2500 kips, and we'll do this right. Add, do it right here, I also want to see the load values. So that's good. See what I'm doing. As you can see, the arrows are relative to the size of the forces. So bigger force, bigger arrow, smaller force, smaller arrow. So we're going to go ahead now and close this. Let me see, is there anything that I've forgotten to do? No, tutorial, negative 200, negative 2500, IXXE, that. Okay. I think this is everything, so we can go ahead and run the calculations now. So we go to results, diagrams for bars, MY, apply. Okay. As you can see, for the vertical, just the vertical, we have a maximum moment of 5,000 and a minimum of negative 5,000, which occur at the ends and the middle, which should be the same as a linear case, which it is. And if we go to a nonlinear case now, we get a maximum of 7,976 and negative 796. So let me go to the results real quick. As you can see, for first order, which is the linear analysis, we get negative 5,000. Well, sorry, I never really clicked on linear, but yeah, it's 5,000 and negative 5,000. So these occur at 0, 100, 5,000, and 200. You can just, it's down there. And then for the second order, the exact solution produces 7,987 kips. Sorry. We'll go to nonlinear, 7,976 kips. So as you can see, robot doesn't give you an exact solution. This could be for a couple of reasons. One, because they don't compute it exactly, and two, because of things like the having one for the shear area, and that sort of stuff will throw off the results a little bit. But this is good enough for engineering applications. Because remember, this is kip inches, so 10 kip inches is not that much. Also, if we'd like to see the deflections, here, the deflection for the nonlinear case, second order case, is 2.469, and my exact solution was 2.390. For the linear case, the solution was 1.3889, and the exact one was 1.3889. So robot did a very good job in computing the deflections and the forces on the member. To see the results, you can go here and click on forces to see it in tabular form, and it'll come up. It'll show you which node it's on. Bar, they're all on the first bar because there's only one bar. On which node it is, why they're either the first or the second. To show you though, there's no the maximum positive moment isn't shown on here. That's because we don't have a node in the middle. If we had a node in the middle, then you'd be able to see the maximum positive moment. There are other ways to get around that, but I won't go through that in this tutorial. So we go ahead and close that. I think that is all. Yep. If you guys like this video, just share it, comment, tell me what you think. This is my first video on how to do analyses in robot structural analysis. I did this video because it was very difficult to find analyses in English, and I think that robot is a very good software because of its interoperability with Revit and other Autodesk products. So like, comment, share, tell me what you think, and I'll try to do these on like a weekly or bi-weekly basis and post them as quickly as possible, but I'm really busy. I can't make any promises. So until the next video, you guys have a good time and don't forget to save. Thank you.